Today we begin a very large topic, the topic of pollution. And under this heading we will be examining issues with air pollution, water pollution, and pollution of the soil. We'll also be discussing remediation efforts so that when we pollute an area, what can we do to fix that? And we'll also be talking about the topic of sustainability and how to do things in such a way that we don't pollute. So let's begin with air pollution. So by air pollution, I mean those substances that are emitted into the air as a consequence of human activity, which in one way or another are toxic. And we usually divide air pollution into two types. The first is primary air pollution, which refers to materials that are emitted directly into the atmosphere as a consequence of various kinds of activities. So things like sulfur oxides and hydrocarbons can be sources of air pollution, as we'll see. We'll talk about them in much more detail. But then there's another category called secondary air pollutants. And these are pollutants which are a consequence of primary materials being chemically acted upon once they are in the atmosphere to form new classes of pollutants. So things like ozone and certain of the sulfur oxides, such as situations where hydrogen combines with sulfur oxides to form sulfuric acid. So H2SO4 is indeed sulfuric acid. So let's begin with the nitrogen oxides, which include nitrous oxide and nitrogen dioxide and dinitrogen oxide. So these are produced via reactions between atmospheric nitrogen and oxygen, generally at high temperatures. They are all in that class of chemicals called greenhouse gases, in that they can trap energy from the sun. They also can produce a substance called photochemical smog, which in the presence of light energy from the sun produces this stuff that accumulates close to the surface of the earth. It can also lead to acid deposition when nitrogen oxide compounds form nitrogen acid compounds like nitric acid, for example. Sulfur oxides are another class of air pollutants, including sulfur dioxide and sulfur trioxide. And these are produced via reactions between sulfur and oxygen. And they are involved in the manufacture in the atmosphere of substances like sulfuric acid, H2SO4. When water molecules come into contact with sulfur oxides, sulfuric acid droplets can form. And this leads to acid deposition on the landscape. When rain moves through this substance in the atmosphere, it picks it up and deposits it on the land and in the water. And we'll talk a lot more about acid deposition later on, but one of the things that it can do is to damage plants. It certainly can also harm animal life, as we'll see. Here's an image of North America that was made by a satellite examining air pollution concentrations. This NASA image illustrates that much of the concentration is across the northeastern part of the U.S. And not surprisingly, this part of the U.S. is also subjected to some of the worst acid rain problems in the country. Here's a National Oceanic and Atmospheric Administration graphic that shows a natural source of sulfur oxides in the atmosphere coming out of volcanoes. In this case, sulfur dioxide and ash and hydrochloric acid are getting manufactured. And the sulfur dioxides in the presence of water vapor will form sulfuric acid. So during rain events, sulfuric acid, hydrochloric acid can come out of the atmosphere then. Notice that a lot of this chemistry is actually going on in the upper layers of the atmosphere, in the stratosphere. But it is what goes on coming out of the troposphere that influences the land and water. Now, this is a natural source, but of course human activities, various kinds of industrial processes, things like burning coal and so on, can also release pollutants that make it into the atmosphere that can contribute to acid rain and phenomena like that. Now, here's another satellite image that illustrates the distribution of sulfur dioxide in the atmosphere over North America on a particular summer day. Another major class of air pollutants would be the carbon oxides, which include things like carbon monoxide and carbon dioxide. Carbon monoxide is a rather toxic substance for oxygen-breathing organisms. It does things like combine tightly with hemoglobin molecules, thereby supplanting the hemoglobin's ability to absorb oxygen. So in essence, it suffocates organisms that it comes into contact with. Now, carbon dioxide, which is, as you all know, a byproduct of metabolic activity, is a substance which also functions as a rather potent greenhouse gas. Not the most potent, but a significant source of trapping solar energy and reflecting it back towards the Earth. Another class would be the hydrocarbons, which include things like CH4, methane, and these kinds of compounds can also be involved in the production of photochemical smog. When we have nitrogen oxides and hydrocarbons in the atmosphere in the presence of the energy from sunlight, we can have the kinds of reactions occurring which produce smog. Now, methane is a commonly produced product of biological activity. So when animals produce waste, some of that will be produced as methane. Decomposition of organisms can also release methane. And methane is another greenhouse gas, a more potent greenhouse gas than is carbon dioxide, however. Now here's a graphic from NOAA that illustrates some of the ways that carbon gets into and out of the atmosphere. So for example, photosynthesis pulls carbon dioxide out of the atmosphere, whereas respiration puts it back in. Every time you breathe out, every time a plant respires, it puts carbon dioxide back in the atmosphere. But as photosynthetic organisms like plants carry on that process, they use it to manufacture things like carbohydrates. Decomposition, such as decomposition of animal wastes and things like that, can put carbon dioxide back in the atmosphere. Burning, so things like forest fires or range fires, will also release carbon dioxide back into the atmosphere. Burning fossil fuels will put carbon dioxide that has long been locked up beneath the Earth's surface. That can also put carbon dioxide back into the atmosphere. And then through various kinds of processes, some of these kinds of sources can be pulled out of the atmosphere and put away again. Oceans, for example, have an enormous capacity to dissolve carbon dioxide, forming the weak acid carbonic acid in the process. Activities like tropical coral reef building will also pull carbon dioxide from various sources and turn it into calcium carbonate. Here's an interesting graph produced by NOAA that illustrates atmospheric carbon dioxide concentrations over the course of a year. Notice that during parts of the year, the concentration goes down, whereas in other parts of the year, the concentration goes up. Notice that during the summer months, carbon dioxide concentrations start dropping in the atmosphere during that time when the northern hemisphere is experiencing summer. So when lots of photosynthesis is going on in the northern hemisphere. Keep in mind that much of the world's land masses are north of the equator. So, in other words, much of what's being done to pull carbon dioxide out of the atmosphere happens during the northern hemisphere summer. During the northern hemisphere winter, when all that land's photosynthetic capacity is declining, then carbon dioxide concentrations in the atmosphere go back up. Here's more satellite imagery that examines distribution of carbon monoxide during 2 years. Notice that China during 2004-2005 had a strong concentration of carbon monoxide in its atmosphere. And then, strangely enough, also in the northern portions of North America, we see during one of those 2 years a high concentration of carbon monoxide. Now here's an interesting graph from satellite data that illustrates that if we look at methane concentrations in the atmosphere, they are greatest going towards the poles and lowest near the equator. Here's another graph based on satellite data that shows that over time, methane concentrations in the atmosphere have leveled off. You can see that in the upper graph. And by the way, the methane concentrations are measured in parts per billion. So it's present in only small amounts in the atmosphere, but because it is such a potent greenhouse gas, its contribution to warming of the planet is not to be ignored. In the lower graph, we see that the rate of increase has declined over time. Now let's turn our attention to another class of pollutants, ozone. Now, ozone occurs in 2 different kinds of ways in our atmosphere. There's the stuff that's in the lower atmosphere, the troposphere, which is largely human-produced via photochemical reactions between nitrogen oxides and hydrocarbons. And so it is a major component of smog. On the other hand, you have what goes on in the upper atmosphere, in the stratosphere, which is a consequence of high energy radiation coming in from the sun, ultraviolet radiation interacting with atmospheric oxygen and forming ozone in a different kind of a way. And in this case, the upper atmosphere's ozone is not a pollutant but a good thing, because by absorbing this ultraviolet radiation, it protects the Earth's surface from high concentrations of ultraviolet radiation. Here's a NOAA graphic that illustrates the stratospheric ozone versus the tropospheric ozone, with, in the case of the troposphere, the source being various kinds of human activities like burning and industrial processes and things like that. Here are categories for air quality with respect to ozone. Notice that the greens are at the good range, very low levels, and the reds and purples are at the bad range, which are not good for people. Notice that the kinds of consequences of people breathing ozone are problems for people who have respiratory diseases such as asthma. Notice how those colors correspond to this map of ozone concentrations in the atmosphere, again based on satellite data for a particular time period. So of course from one day to the next and from one season to the next, this is going to vary. But in this case, you can see that the southeastern US and southern California had the worst air quality with respect to ozone. Here's a related kind of an image that also looks at ozone concentrations across the US, although it's a more generalized kind of an image in this case because it also considers particulate matter, which is something that we'll talk more about later on. On this particular summer day, notice that the concentrations were greatest in the northeastern part of the country, the upper Midwest and into the Northeast. Notice that western portions of the country were largely spared these high concentrations of ozone, except for Southern California. Now let's turn our attention to what goes on in the upper atmosphere with ozone, the phenomenon of ozone depletion, which has been noted since the 1980s, when a seasonal hole first appeared in the stratospheric ozone layer over the Antarctic. If we look at how that happened, it has to do with human activity. Chlorine and bromine containing compounds, notably chlorofluorocarbons, which are propellant chemicals which were used in spray cans, the so-called CFCs. These find their way to the upper atmosphere after people have used them, and they catalyze this breakdown of ozone. So as the ozone in this upper atmosphere is depleted, that permits high energy ultraviolet radiation to reach the Earth's surface at a much higher concentration. Ultraviolet radiation is often thought of as being the principal mutagenic agent on planet Earth. It is the stuff that has driven evolution over the long term, many people would say. But in the short term, what it does is to produce bad things like cancers, especially things like skin cancer, cataracts, which is a situation where the lens of the eye clouds over, immune disorders. It also has been linked to reduced productivity in aquatic ecosystems. And in general terms, it causes damage to DNA in living organisms. Here's a graphic of this situation showing the CFCs making their way into the upper atmosphere where they destroy ozone molecules, permitting greater concentrations of ultraviolet radiation to reach the Earth's surface. Now, ozone depletion over the South Pole is an issue which is rather interesting and worthy of our further discussion. This phenomenon is noted in the South Polar Spring, when sunlight first returns to that part of the planet. Now, in spring, you have atmospheric patterns developing called a circumpolar vortex, which is a circulation pattern that isolates polar air from the rest of the planet. So you have this cold polar air which causes clouds to form, and these clouds have in them this chlorine and bromine, which is a consequence of human activity, and this stuff clings to the ice crystals in these clouds. As sunlight reaches the Earth's surface, it provides the energy to catalyze the chemical breakdown of ozone. When ozone encounters these compounds. Now, this problem was recognized some decades back now as being a significant one that needed to be dealt with. And so in 1987, the Montreal Protocol was developed, which was an agreement among nations that CFCs would be banned from most uses. And since the late 1990s, they have been largely phased out of production around the world. And so what we've been seeing since that time is that the ozone depleting chemical concentrations in the upper atmosphere have started to decline, and so that the ozone layer is now recovering. Here are some satellite images that illustrate the ozone hole over the South Pole. Now, October is the South Polar Spring, and this is that time when the atmosphere over that part of the planet is isolated from the rest of the planet. And it's during that time that you see this ozone hole developing. Now, these are reasonably recent images, as recent as 2010. So the ozone hole is still forming over the South Pole. It's not gone yet. On the other hand, if we look at December 2010, the ozone hole has pretty much closed. An additional source of air pollutants are particulates. These include things like soil particles, soot from burning, salt crystals, various kinds of organic chemicals, things like that. And some of these particulates may contain toxins. So things like lead dust, for example, qualifies as a toxin, as does asbestos dust. Now, most air pollutants are measured in parts per million, or as we saw in our last example with methane, in parts per billion. However, particulates like lead tend to be measured differently. They're measured in micrograms per cubic meter. Here's a graphic that illustrates how it is that particulates get into the atmosphere. Notice that volcanoes are a significant source of particulates. And we also cannot ignore what comes in from space, meteoric dust. However, in addition to that, we have human activities. We're going to end today by discussing acid deposition. We've talked a little bit about it already, but let's formalize some of this discussion a bit. We're talking primarily about sulfuric and nitric acids, and we've already seen how they can form from sulfur oxides and nitrogen oxides. Sulfur oxides often come from burning of coal, and nitrogen oxides can come from things like internal combustion engines. And so the nitrogen oxides from the engines combine with water vapor to make nitric acid. So these materials find their way into the atmosphere, clinging to particulates, clinging to water droplets, and then are flushed out of the atmosphere by precipitation events like rain and snow. And these materials then get into the soil, they get into water. So what we've seen across the northeastern part of the United States is that many of our lakes have become acidified as materials have blown from the Midwest to the Northeast. And as it's been precipitated out of the atmosphere, it's accumulated in bodies of water and acidified them to the point where a number of kinds of fish can't even live in these lakes anymore. One reason would be that as acidification occurs, toxic materials become soluble. So certain kinds of metals, for example. And this can make a less hospitable environment for certain kinds of organisms. Acidification also leads to the leaching of calcium from soils, as well as potassium. And these are nutrients in soils, and so as they are lost from systems, this results in reduction in soil fertility so that certain kinds of plant life can no longer survive in these soils. One phenomenon that can be related in soils to acid deposition is the release of aluminum in such a manner that the aluminum reaches toxically high concentrations for a number of different kinds of organisms again. Now, changing the chemistry of the soils can do things like damage trees. Conifers are particularly susceptible to this. And many of the conifers at high elevations in the mountains of New England have succumbed to acid rain effects. Also in the Adirondack Mountains of New York State, many of the high elevation conifer groves have died out as a consequence of acid precipitation events. Now, another phenomenon that can happen is that pea relatives, the legumes, can be negatively impacted, in particular by soil being exposed to acidification. This can influence populations of the nitrogen-fixing bacteria that live in association with leguminous plants. Now, once acid deposition effects have occurred, it can take ecosystems a very long time to recover from them. Once nutrients are lost from a system, they're not going to be rapidly built back up in these systems. Once trees have been killed, it takes a long time to grow new trees. So with that, I'm going to stop at this point. We're going to talk a little bit more about acid deposition next time.